This conference will now be recorded.
So welcome everyone. Today we're going to have again another talk, this time from Timebeat.app. Before that, I wanted to just go through some regular things with TAP. So as you know, we have the 4 work streams, and we're looking at two of them are pretty much like in parking mode right now. Basically, they achieved the goal. And we were talking to Alon Regev from Keysight to see if he will agree to have, let's say, one work stream for servos. And anyone else, you guys have an idea, please come forward. We'll figure out how we can squeeze it in, turn it to another work stream, and we can continue basically working on that. And also with the mailing list, please join the mailing list. You can find it again on ocptap.com. So we can keep this, we have the mailing list, basically use it to its capacity. So again, today we have Lasse. He's going to basically present to us the latest about developing a P2P-based overlay network for auto discovery, configuration, and setup of PTP sessions between server nodes. In the description, it says it will allow time hierarchy and dissemination to be based on a cumulative error of source, and for nodes to compare, report, verify time from multiple sources with using IEEE 15.8 capability in server and network without reinventing the wheel. So a little bit about Lasse. He's been working with network and systems for over 20 years and has for half a decade been working with high accuracy clock synchronization as time as a service. So Timebeat.app is a third PTP stack, and he is currently working on improving the scale and accuracy of time distribution using PTP. So if there is anything else, someone wants to bring up, any comment, anything you want to add before we hand it to Lasse for the presentation? Nothing? Very great. Lasse, with no further ado, the floor is yours.
Thank you. So I guess when I press the screen thing, it says I have to get the organizer to make me presenter.
Oh, okay. Let me check it.
Oh, there we go. Okay.
You are, yes.
Ooh. So can you see the first slide in the presentation?
Yes. So everyone else, please mute your microphone so we'll minimize noise.
Okay, yeah. Okay, cool. Yeah, what we sort of experienced as we were making Timebeat and making improvements to it is that we now have the capability of achieving near lossless synchronization between nodes that are running Timebeat. Okay, so this is using commodity hardware and not taking in quotes advantage of the capabilities of network switches, boundary clocks, transparent clocks, this type of thing. And okay, the typical performance, okay, it depends, but it's not uncommon for us to see something like plus minus 5 nanoseconds in this type of scenario where we have just one server with a NIC connected to, in this case, an Arista switch, and then connected to another server with, okay, here's a solar flare. So that's kind of cool. And then we sort of considered a little bit what were the implications of that. Okay, so I just want to talk about how to get, how did we manage to achieve this accuracy? Okay, so it's sort of a modified lucky packet approach. Okay, so what we do is we observe what is the unidirectional latency between nodes, and then we assume that at least in the short term, this is going to be a constant value. Okay, so if we know that, okay, you get to a position where if you observe the difference between T2 and T1 in PTP, or the difference between T4 and T3, okay, if you see some difference between them, which is sort of lower than what you know is the minimum unidirectional latency that you've observed, okay, you can deduce that it's because of an actual offset between the two clocks in the two servers. Whereas if it's higher, okay, you cannot make this assessment because it can be due to some type of network buffer, okay, a queue in a switch or in a network card. And so, yeah, so this allows us, let's say we have a graphical illustration of this, where we move from the very monochrome view of the world to being able to filter out, you know, what's a good PTP transaction and what's one that we should ignore because we're not completely certain what it means. Yes, let's say here we explain the lucky packet basis, okay, which is largely what I have just said, that we're able to separate these PTP transactions, which for sure is due to an offset, and those which may or may not be, okay, and this has made the software extremely accurate. Okay, and yeah, I guess it's important to note that we achieve this without having to invent a new clock synchronization protocol. Okay, there's essentially nothing wrong with PTP. We don't have to devise new strategies where we're sending 100 packets per second between hosts, and in some fashion look at the spacing between them and then passing it off to a machine learning algorithm to do any deductions, and it can use the hardware which is already present in hosts and switches and so on. And another advantage when you become more selective about what offsets do you process is that you know, you don't have to, if there is some change, okay, because of congestion in the network, if the load goes up, you don't have to change it, okay? So in many PTP clients, you'll just see the variance sort of grow, and it's actually because the underlying servo algorithm is chasing a big asymmetry, but we can sort of completely avoid those. And there's a link here to some post I did about you know, how Timebeat compares to PTP4L, for instance. Okay, and then I just wanted to make the point here, I guess. So I did a long video of you know, an oscilloscope just showing that you know, in fact, this is the you know, that the values we are presenting are good. Okay, and I will spare you the 8-minute video of you know, an oscilloscope because it's not particularly interesting. But essentially, we do essentially to say that it's a claim that we verify, right? So here we have, for instance, a test where we have an oscilloscope. Okay, we connect it to a pulse per second that we're receiving in this case from a COSA QG2 Grandmaster, okay, and then from that one we give PTP first to sort of one host, and then from that host it acts both as a client and a server, right, in a sort of a type of boundary clock, you could say. Then we send PTP onto another host, and then from there to another host, and then we end up in a fourth host where we also have a pulse per second output. Okay, and then we can compare, does the pulse per second of where we started out match the pulse per second after these sort of 4 hubs, right? And this is interesting. And when you do stuff like this, you must test really that it works in an independent way like this. And okay, we do this. Okay, and then we thought a little bit about the limitations of of the classical model, and I will not spend too much time talking about it. Okay, but the classical model is sort of you have a monolithically large grandmaster clock that can, serve lots of clients, and then perhaps in between you have a some infrastructure of some boundary clocks, and every sort of hop in the path is made by different people, and if there's some error introduced, it's not particularly transparent to the the ultimate consumer of the time, some servers in this case. Okay, so yeah, so this was interesting, and so based on all of these thoughts, we wanted to do something a bit new. Okay, so we decided to stick with PGP, but add to it some intelligence we call squared. So if we look at the difference, right, between the classical model and how we think the future looks like, we think it's going to be slightly different, okay, in a sense that there's going to be sort of more sources of UTC available, okay? They could come from smaller grandmasters like the Kelsar QG2. It could be things like Silicon SDS cards, okay? And there'll be lots of paths for time to traverse, okay? It doesn't have to be sort of this head end that is currently the case. And with this sort of increased mesh of servers and paths and time sources, okay, comes some opportunities to compare time in different places a bit more, and we think this is quite an attractive option. And of course, I will also pitch the timing cat. Okay, it's the same thing. So you have this sort of commoditized open way of putting GNSS receiver and oscillator in a server. And we certainly welcome that. I think this is very interesting. So what is squared? Okay, so if we first think of just the most basic example we can think of, or let's say, let's do the bullet point. So it's something, okay, that establishes a peer-to-peer network, okay, between different nodes in the network. And I'll go into how this network is established in more detail. But for now, let's say it's something that establishes this network. Okay, you can then, using this overlay network, tell different nodes that using PGP, one is going to be a source of PGP, one is going to be a source of time, and one is going to be a consumer of time. And in this model, okay, every node in the network can be a source of time and a consumer of time, or typically both, right? So there is a way to announce who in the network has capacity, so that if a particular node is able to give time to some other node, okay, you can sort of you get messages like this sent, and yeah, it's domain oriented, so it uses standard PGP subdomains. It creates a hierarchy for how time is disseminated, and the hierarchy is automatically set up and managed sensibly. It has the concept of what we call preference goals and reservations. Okay, so you can sort of modify the topology a little bit, and I'll go into detail on when this can be relevant and how it's achieved. And then it allows to compare lots of different sources of time, okay, to verify that they agree and alert if they do not. And then it has the concept of reputation scores, which is when clients of a particular node report back to that node how time compares to other time sources they see. And I'll get into more detail about that. Yes, here's a basic example. Okay, we can see server A, maybe it has some type of UTC source. It could be a pulse per second input from some type of GPS disciplined oscillator. Okay, and it's configured to make 4 sort of seats available. And you have this peer-to-peer network. Okay, so on server B, you can see that server B has seen that okay, this capacity is available, and you can see that it has established a session with server A. Okay, and here it's PGP unicast, which is then running between the two hosts. Okay, can I use the cursor? Are you able to see the cursor if I move it around? And yeah, down here you see that the configuration is sort of very lightweight. There is not a lot to configure other than a few things, and yeah, we'll look more at that as well. So that was a very simple example. Okay, here's an example which is not so simple, and this is sort of where you can get a sense for some of the stuff that Squared can do, which otherwise would be practically not feasible to do, right? So here we have, for instance, 13 different hosts, and this one up here, for instance, it gets in the old school way PGP from a grandmaster, and this one here maybe it gets pulse per second input from a grandmaster. In fact, this is a real example. Okay, I set this up and I took down what all of the path where they went to and from. Then we have another host there, okay, with some different configurations. It can offer time to 4 nodes. It wants to take time from 2 nodes. And then you have all of these nodes down here. Okay, they're actually virtual machines, and they have the same configuration where they say, okay, we want to be able to give time to 4 places and take time from 3 places. And then, yes, Squared, it sets up this sort of hierarchy here, and you can sort of see that. So each of these nodes down here, you can see that they have 3 arrows that are pointing towards them. And yeah, not all of them. Of course, when you have an equality here where there are more seats on offer than there is to consume, okay, you get some surplus. But the benefit is that, yeah, in each of them, you have then 3 sources of time that you can compare, and we'll look at exactly how it works. And yes, of course, if there's a failure, you can switch over and reroute and all of that good stuff. And this is 13 hosts, okay, and there's a lot of arrows in this one, and you can imagine if you had even more, configuring this manually would not be feasible to do at all. So just on the talking about the discovery mechanisms, there are two types of mechanisms that are supported. Okay, let's talk about the lame one first. Okay, so you have MDNS. Okay, it's the same way that you know, your phone finds your Sonos speaker in your house or whatever, but it's very easy to turn on, and you know, port 53 type stuff. It works well for sort of small deployments where everything is on the same subnet. You don't have to think too much about it. Then the other approach, which is far more scalable, is DHT, right? It's a distributed hash table approach. Okay, so for this approach, you can see that you have to initially give in the configuration file a seed list. Okay, so there has to be, when a client starts up for the first time, some initial way that it can find other nodes in the network, and this is what the seed is. And this can be one host, but more sensibly, it would probably be at least 2 or 3, right? And then once the client speaks with these seed hosts, okay, then you have this establishing of a number of connections to other nodes. And then, of course, if after a client has this information about the network, you no longer rely on the seed nodes, right? So if they go away, you're still good, and everything is still talking to everything. And similarly, if you have previously been on the network and so on, other nodes will already know about you and make connections to you. And yeah, so it's sort of this approach, this peer-to-peer approach with DHT, it's sort of extremely resilient, right? It can't get any more resilient. Okay, and then just talking about, so how do we decide what connects to what, right? There has to be some sensible hierarchy so that ultimately, you start at something that has a source of UTC, or there are other options that I'll look at in a second, but and then you connect something to that. So there's sort of a first layer, and then you connect something to that. So you have to somehow find some way of creating this sort of hub cost, right? It has to be based on something. Okay, so this is done in this case using the error of source. Okay, so I don't know how easy this is to understand, but suppose that you have some server here, server E, I guess, right? Or whatever the server is. So it has it's getting time here via A and via B. Okay, so it will always select to take time from the one where it registers the smallest error of source. So when you have BTP running, right, you're gonna see a distribution of offsets. Okay, so if it's 2 hosts connected to each other via an Arista switch, okay, it's going to be a few nanoseconds plus minus, right? And if it's some virtual hosts connecting to each other, then the variance is going to be substantially bigger, right? A couple of microseconds maybe. And so this is what gets evaluated here. The time sources that I'm actually actively using to steer the clock, what's the variance? And then I'm going to announce essentially that this is the error of source that I see. Okay, and then when I send time on to this guy here, for instance, okay, he's gonna know what is the error of source that I see, and he's gonna add on to it so that as we go along in the chain, it becomes cumulative, the error of source that he sees. Okay, so he's gonna take whatever this is plus whatever error is introduced here, and this is going to be what he announces, right? And then this guy is going to do the same thing, so that the more hubs there are, the larger this cumulative error of source becomes, so that if you're a node that has just started up and you're looking for time, right, you can choose to go to the guy who has available capacity, which has the smallest error of source, okay? And similarly, because this is dynamic, okay, because if you're connected in a chain like this and something changes, you can decide to switch from one node where you're getting time to another node where you're ready to get time from, and I'll show how that works. So it has the effect, okay, that in a network, okay, where let's say this hierarchy was real. Okay, suppose now somebody starts to download a large file from this guy, right, or this guy, or whatever the case may be. And this introduces a larger error because of congestion, or whatever the case may be. This guy can then see that this is occurring no matter where in the upstream path it occurs, and then the network can converge around it by selecting other paths that have a lower sort of error of source and the cumulative error of source. And yeah, here I note that on top of that, if you want, you can also configure, you know, some static cost to each hop, and there are options for penalizing software timestamping in favor of hardware timestamping and so on. But the bottom line is that because you have this cumulative error of source, okay, all the way through the chain, no matter who consumes the time, he has a good understanding of what is the cumulative error of source from whatever UTC source was originally, okay? And this is useful information, and you can make decisions based on it, not just for timekeeping, but for other things as well. Okay, and yes, I guess here's some CLI stuff we can just briefly look at, right? But it's you can see here, for instance, we're on a particular host, and we look at the servers in quote that we're getting time from, and we can see this is the cumulative error of source that has been passed along, which they hadn't observed, and then on top of that you have the error of source that we observe between us and them, right? And so this is where some nodes are connected to you and actually giving you time. And similarly, we talked about this capacity announcement thing that's going on, where nodes that have available capacity are indicating that they have that available capacity. Well, here, okay, you then see the available capacity, but you can also see what is the cumulative error of source that node has, okay? Which is why you can see that the higher numbers, okay, if everyone here originally had 4 seats on the go, right? You can see that the ones with the higher cumulative error of source, okay, they still have those seats left. And of course here, if another seat needs to be consumed by someone, okay, you would choose to take it from, say, this guy here who has the lowest one, okay? And then, as we go along, like I said, if anything changes, okay, constantly we're evaluating from this hierarchy, what should we be doing, okay? So there are sort of 3 tiers. You have some hosts which you have a PTP session with, okay? And let's say you have 3 PTP sessions where you're getting time from other nodes. Okay, then maybe you keep 1 or 2 of them in an active state, okay, where you actually use the time that you're getting from them for the purposes of adjusting your clock, right, for your servo. And then you have maybe 1 or 2 of them, which is in a monitored state. So you're running PTP with them, but you're not using the input from them to actually adjust your clocks. Okay, and then you try and keep it. Let's say the software try and keep it so that if it turns out that the error of source, the cumulative error of source that we see from the ones which are monitored, if it becomes more attractive than the ones we're using, then we switch, right? And this is actually what this is better factor in the config in the config option. You can see it's set to 1.4. Okay, it's how much better does it have to be before we switch to it? And similarly, for those other nodes in the network that we are not currently doing PTP with, but we're not taking PTP from them, we still keep an eye out to see if there's something better than what we have, right? So that those sources that we're currently getting PTP from, but we're only monitoring them, we're not using them for steering. If it turns out that there's an available source somewhere that's doing a better job, has a lower cumulative error source than them, then we'll add them, and once they're added, we'll take out the one which is not so good anymore. Okay, so it's sort of dynamic like that. Okay, what's the attraction? I guess this is sort of a little bit self-evident. But yeah, you can have sort of this network which is self-configuring based on where's the quality of time actually compelling. You can imagine that it scales quite well because you have this sort of hierarchy where everyone is a client and a server. And of course, you can also decide, that okay, maybe you have one server that's doing something which is important. So it doesn't have to also provide time to other nodes, right? So you could have one that just consumes time, but you don't want to spend resources on it, also giving time to others. So you decide, it could also be based on the hardware capabilities and so on. So you decide how much capacity, how many sources you want to see concurrently, and how many you can sort of provide time to, and that number could even be 0. And similarly, you also decide the concurrency, and we'll get to that. Yeah, so it's different from building a big grandmaster clock. Okay, instead it's sort of more distributed. And you can imagine, because of the geometric nature of the sum, that even if you just have from the UTC source to the last link in any chain 3 hops, because we show that okay, synchronization is quite good, you will still have good synchronization. It will be quantifiable because you know what the error is, and you know that if anything changes on any of the hops, okay, PGP squared will just converge around it, because it will discover that now the variance in one place grows and it becomes sort of an unattractive path. And yeah, so what's the architecture? Okay, we use something called lib P2P, and then there's a protocol on top of that for conveying all of this information based on protocol buffers. For the capacity announcement system, okay, one has to be a bit careful, okay, because if you imagine a network with a lot of nodes, okay, if everyone who has capacity is sort of sending that information to everyone, all of a sudden you have a lot of traffic. So we manage this very carefully by using something called PubSub, publish subscribe, which is sort of a clever way of managing message routing in a peer-to-peer network to sort of keep the traffic volumes down, so that and similarly, if you don't have any capacity available, then you're not going to announce that you don't have any, and so on and so forth. And it can be segregated into different domains, and I can explain more about that. Yeah, and then so there is this PubSub type network for essentially what is a broadcast of capacity announced messages. And then this means that nodes, there's no requirement for every node to have a connection to every node. Yeah, but then when you want to consume some capacity from someone, okay, you set up then a direct connection between the two nodes, so you can negotiate PGP sort of settings that you'll both use. And yes, it's all very X509-ish, right? So there's everyone has a public key which goes along with messages that they send, and a private key for decryption. Everything is signed and authenticated, and so on, so that you can be certain that when you read some information in a message, when somebody says, I have capacity available and this is my IP address, for instance, you can be certain that the message is authentic and it hasn't been tampered with in transit. Okay, and yes, like I said, here's an example of a geometric sum, right? So you can see that even if we have just a few hubs, here we envisage that everyone has time from 2 places and is able to provide time to 20 places. Okay, even within just a couple of hubs, you are able to support an awfully large infrastructure. I'm now going to talk about the specific features of Squared. Before we do that, I'm aware that it's very difficult to gauge the mood of the crowd. Is there any questions at this juncture? No? Okay, well, I shall just continue then. Okay, so the first one is domains, right? So PTP has the concept of domains, right? So we want to take advantage of this so that in different locations, you can use different domains if you want, or you could have one domain for one thing and another domain for another thing. And then, a host or a node can be in as many or as few domains as it wants to. And of course, this allows you to it could be like a boundary clock, or maybe like a BGP gateway would be a better way of thinking about it between different things. And you can also contain, the messages inside those domains to, other nodes which are there and so on. So it allows for things to be segregated in that fashion. Okay, and then PTP intervals, and this is the first time I'll just mention this. In a second I'll mention it again, but it's just PTP ultimately, right? So if you have one node and you say, for this one, okay, one transaction, PTP transaction asynchronous, okay, I'll set that to interval 0. Okay, of course, it will just in the standard section 16.1 way negotiate that, okay? And then maybe in another place you have another type of host and you want the PTP interval to be shorter, okay? So maybe that one you whack it up to 16 or whatever the case may be, so you can configure that, which is kind of cool. And then we have the concept of concurrent sources, okay? So if you want, you can you can decide how many sources do you want overall, and how many of them do you want actually to use to synchronize clocks from. And this can be an arbitrary number, but you can sort of see the diagram on the left-hand side. The yellow dots is a source we're only monitoring, and the red and blue one is one that we're using for sync. And then conversely, you can see that on the right-hand side, we have one where there's 2 concurrent sources. Okay, and so how do we deal with that? If in any given sort of interval of the servo, they have to make an adjustment. Okay, if we have 2 offsets from 2 sources, okay, we just calculate, okay, based on that, what's the median offset, and then we choose that to stare from. Yes, and again, what happens to be the source that you stare from, and what happens to be the sources that you monitor, is exclusively a product of like I said, the error of source. So it will be optimized and it will be changed as and when conditions in the network change. Okay, so here's an example of this, the path optimization. This is quite a crude example because here we just switch off a source. But it's just to show what happened. So here we imagine that the host we've denominated as .2 is getting, has a UTC source, in this case, in the form of a 1 pulse per second input. Okay, so it's providing this to .4, and it's providing this to .3, and you can see that in addition to that, .4 is also receiving a feed indirectly from .3, which happens to have a high quality oscillator. Okay, so this is a capability of squared that I'll just get back to, but now increasingly we sort of see that network cards, some network cards, let's say high quality network cards, okay, they now come with increasingly better oscillators, okay, and this trend will continue. And so we want to be in a situation where, suppose we have a UTC source or several, and they all go away. Okay, we want to make sure that the squared network converges in such a fashion that the root nodes where we're taking time from in that scenario, of course, becomes the nodes that have those high quality oscillators. And we'll get back to the capabilities thing here, but you can sort of see it here where you see that 3 has a high quality oscillator, and this is the number of nanoseconds it's going to drift in 24 hours. And the UTC source is indirect, and conversely, that 2 has a UTC source and it's direct. Okay, so now to create the slide, if you like, or to perform the test, okay, we pull the plug on we pull the plug on the coaxial cable, right? So now no more pulse per second input, no more UTC source. We're now UTC sourceless, right? So what happens? Okay, so now, and this is seen from that force perspective. Okay, we are we see that the capabilities have changed. Okay, in the paths, there is no longer a UTC source as that was up here. We now just have the high quality oscillator, and you can see over here on the on the graph, okay, that we stopped taking time from this guy and we switched over to this guy, and this is in nanoseconds, right? And you can see how performing that switchover was not associated with an increase in error as it was observed. Okay, and this is because we come back to this modified lucky packet based approach we have, right? Because we were already monitoring the other guy, that 3 in this case, we already had a good understanding of what is the unidirectional latency to .3. So our filter was already filled up with data that allowed us to compute this information, and so the failover was not associated with a degree of error, okay, which is kind of cool. And then one could ask, yes, but in this case, okay, why didn't we just start to monitor .2 as we were now taking time from .3 instead, okay? And the answer is this is actually what happened. We just didn't show it in the previous slide. So before we showed only this guy here and this guy here, but you remember before when .2 had a UTC source, okay, it was not sensible for .2 to consume time from .3, and you cannot both give time to a node and take time from a node. Okay, so we had to reverse that sort of flow, because the root in our squared network is now the host that remains with the high quality oscillator. Okay, so we had to reverse this flow. And then after that flow was reversed, it again made sense for .4 to use .2 as a backup in case a cable between the two of them are pulled or whatever the case may be. And so this is sort of what we can see actually happen here. So instead of just displaying this and this, okay, we can now see that .2 actually came back okay, and it's now being something that we monitored. And we can also see, like I said, that the capabilities for both those paths now no longer contain a UTC source, but they contain information about the high quality oscillator available. Yeah, buddy. Okay, and then there was the business of PTP intervals, which I just wanted to touch on again. Okay, so of course we should do some CPU-friendly stuff, right? So because it's all just PTP and unicast and negotiated in the standard way, okay, with the normal messages, we have also the option, and I just want to show it here, okay, to have different intervals when sources of time they play different roles for us, okay? So if we're just monitoring someone because we want to have a rough idea of you know, what's the error of source between him and us, and you know, is the time that he provides, does it roughly agree with the time that other sources are providing? Okay, we don't have to run we don't have to run PTP at sort of a hysterically high packet rate, right? So we change it on the fly, right? So if we decide to take a source from the monitored only state into an active state, okay, you can literally see the PCAP dump here, right? You see, okay, here we are taking along, right, at interval 0, you see. You have your sync, your follow-up, and your delay request response going once a second, right? And then here the change happens. Okay, now we want to switch from monitoring to active. Okay, so we just do the normal signaling messages with the relevant TLVs. Okay, and then down here, okay, we have now moved from you know, one transaction a second to a higher value, right? So yeah, I guess that's kind of cool and very CPU friendly. Okay, and then we talked briefly about these capabilities. Okay, here's the full story. So, you know, we have these paths that form in the squared network. Okay, and there are currently two capabilities that we have implemented. Okay, one is the UTC source, and they come in the flavor of either direct or indirect. And the other one is the high quality oscillator. And of course, for oscillators, we should take advantage, not every oscillator is the same, so we should take advantage of the fact that some oscillators have a better holdover capability than others, and this is measured right in what is the drift that the oscillator can experience over the course of 24 hours. So when we decorate the configuration file with information that, you know, our network card has a particular oscillator, then you know, PTP squared takes this into account, right? So if we have a path where we have a UTC source here and then an oscillator that drifts by maybe 4 microseconds in 24 hours, and here one that only drifts by 1.5. Okay, as this path is created, and as we pass information down it, you know, ultimately this guy here, okay, has to decide of the different nodes that he's connected to, and this is just one of them. Okay, in the path, which one has the best capability? You know, if there is, you know, if he has a choice of different paths through different nodes, Okay, he will always select a path that has a UTC source available, right? It will make no sense for him to select a path that only had a high quality oscillator, but no UTC source if another path had a UTC source. That'd be crazy, right? So that's sort of the first thing he thinks about. And then the second thing he thinks about is, okay, but if UTC sources are gone, okay, which one has the best oscillator? And I have to say, perhaps this is not the best example I could have chosen, right? I should have really put the 1.5 microsecond oscillator here and the full microsecond oscillator here, because what he would have seen would have still been the 1.5 microsecond oscillator, right? So we simply optimize what's the best capability available in the path. And yes, in BGP, we would call those attributes as they're passed down transitive in nature, right? So that's capabilities. Okay, and then we come to reservations. So what's a reservation? Okay, so we can massage a little bit how this hierarchy gets established by using reservations and preference scores. Okay, so suppose we have some source of UTC here that supports a certain number of clients or can give time to a certain number of nodes. That's really what that means, right? You know, maybe in our network, okay, we have 100 trading servers, and we would like very much for them to always be able to consume that capacity before we give it to these 847 not very important virtual machines over here, right? So how can we do that? Suppose we first started up these guys over here and we didn't have this system, right? They might decide just to consume all of the available capacity here, right? So if it's available, they'll take it, okay? Unless we create these reservations. So reservations is something where on some servers, okay, we configure a particular preference value, and then on particular other servers, we say, okay, some of our capacity, we only want to, 50% of the capacity or 25% of the capacity we have, we only want to give it to host that percent with a certain preference matching that, okay? And it's not limited to sort of one reservation. It could be different tiers and different scores. And here's an example of that. So in this example, for instance, okay, we've configured a preference score of 750 here, and then we've told this guy over here to reserve 25% of his capacity for clients that present with a preference score of 500 or above. If he has, in this case, 8 seats to offer, it means that the 2 seats will be saved, okay, and the other 6 will be available to, there's always like a default allocation, which puts the rest of the capacity in that allocation. And for that reason, you can see how it has then been the case that these guys over here, okay, they have, when we do this showed squared reservations, consumed the 2 seats that were reserved, and these guys down here, they have consumed the rest. And even if these guys are started first, they cannot consume the capacity which is reserved for them. So it stays available for hosts that have that higher score that may want it. And yeah, I think that's largely what I want to say. Okay, and then we come to the concept of reputation scores. Okay, so this is sort of a little bit difficult to understand perhaps initially, but it's the idea that rather than us just evaluating the upstream quality, okay, which you can do by looking at this cumulative error of source, okay, it would also be cool if we could evaluate how we're perceived downstream, right? So that's what reputation scores is. So if we consider this oversimplified example where A, B, C, and D are each providing time to W, X, Y, and Z. Okay, of course, in the real world, this would never happen. You know, you would have sort of a mix between all of the nodes, but just for the purposes of keeping this example simple. So then if we look at just a particular node in isolation, okay, W. So what's going in at W? Well, W is receiving a time feed from A, B, C, and D, okay? And then what we can do, okay, is we can compare, okay, let's say using a statistical test, okay, the distribution of offsets that we see from those sources. Okay, so if we have 4 sources, okay, we can on W compare A with B, we can compare A with C, A with D, B with C, B with D, and C with D. Okay, so essentially, if you imagine you have a piece of paper, okay, and you draw 4 vertices on it, okay, like the corners of a square. If you have to connect every vertex with every other vertex, okay, how many edges do you end up with, okay? And if it was 4, you can imagine, well, there would be like, first you would draw a square, okay, which has 4 sides, and then you would draw a cross in the middle. So overall, you would have 6 edges. So that's how we sort of arrive at how many comparisons do we have to do, and then we carry out this test. Okay, we cannot assume equal variance. Okay, so the variance of the distribution of offsets that we see from A might, for a variety of reasons, be different from what we see from B, C, and D. But ultimately, we're interested in finding out, even given this, whether the mean is the same, which should hopefully be 0. And what it would infer was that, you know, they all had the same time because the mean was the same. And then based on that, for each of those tests that we carry out, if we draw the t-score, the t-test score, along with the degrees of freedom through the cumulative distribution function, okay, we can calculate a p-value, okay, which will be somewhere between 0 and 1. And let's see, we can then, okay, take this information and feed it back to the nodes that are giving us time, okay? And the benefit of that is that A, B, C, and D, okay, will get a feel for how does the time that they're providing to W, X, Y, and Z compare to the other times that those nodes receive, okay? How does A compare to B? How does A compare to C? And how does A compare to D as observed by W, X, Y, and Z? Okay, I hope this is, I guess it's not so easy to understand. But here is a real world example, okay, of what is actually observed when we perform this test. So here, okay, we have nodes 2 and 3, which are providing time to 4 and 5, and as it happens, 4 is also providing time to 5. And so what we can observe, if we look at the clients on node 2, okay, what they report back to us is how well does the time that we provide them with compare to time that other nodes have provided them with. And here we can see that the reputation scores are very close to 1, okay, which means that you know, the time sources as observed by the clients agree with other time sources. And we can contrast that with an example where here we have put one of the the host's off by a second. Okay, I don't know if you can see that, but here it says 1 second, and this is 0, and this is close to 0. And we can see how the providers of time are then told that actually the time that they provide compares very poorly with time provided by other nodes. And interestingly enough, this is very close to 0.5, okay, which is a confirmation of the old adage that a man with 2 clocks never knows exactly what time it is. Yes, I could go into more detail about this, but it's a bit long here, so I think let's leave it there. Final thoughts. Okay, let's say on the more high level, okay, if you contrast this model of time dissemination, okay, you have here something where any node in the network, okay, gets a very detailed picture of what's going on upstream and how does everything upstream compare with one another, and how does it compare to node B. But in addition to that, because of the reputation score stuff that I just covered, you also get an idea of how is node B perceived downstream, right? So this is really useful, right? Because in the classical model above, right, you only have really the single view of how does this node here compare to this single source here, which might get time from this guy, who gets it from this guy, who gets it from some clock, right? And you only have the visibility here, whereas in this model, you get a picture of everything that's going up upstream and how the error, the cumulative error, what it is when it gets down to you. And you also get told by people you're distributing time to, how does the time you're distributing compare to time from other sources? Okay, so, you know, in this model here, okay, if node A is connected with some SFP that introduces a large asymmetry, you will never know about it, right? But in the second model, right, you will know about it, right? Because you get to compare yourselves with so many other things, including where you're taking time from and who you're giving it to. And you can alert on it, right? And you can reroute around the things dynamically and so on. And so that's kind of cool, isn't it? And then I just want to put a fat line under the fact that squared is just something built on top of PGP. So you can have as much of this in an infrastructure or as little of it as you want, right? There's nothing preventing you from having this in some places, okay? And maybe this can be a UTC source and it's sort of plain old PGP, right? Or PPS, or maybe also as clients, right? This, you know, Timebeat also works as a source of standard PGP, right? So if you have something over here, you know, that doesn't speak squared, okay, it's not a problem at all. It can just consume standard PGP and doesn't have to be square aware, right? And pulse per second and NTP and NEMA. Yeah. So in terms of the deployment scenarios, of course, you could go straight to just putting this everywhere, right? But another option you also have, okay, if you already have a PGP infrastructure, is you can maintain that. And then initially, okay, you can turn this on, okay, and run squared between nodes. So you get a lot of these PGP sessions running between nodes. And if you set the you know, the concurrent sources number to 0, okay, all this will do is essentially just start giving you an idea of, you know, how do time from different places compare to each other, and for the things I'm giving time to, how are they perceived in respect of other things? So that's certainly also an option. And then here is me talking about why we've written it in Golang, and I'm talking about why this is sort of a really interesting and efficient language, and I think we can probably skip that. We are still developing this, okay, and improving it. it does scale extremely well, but we did this because it also provides monitoring on a whole new level and great accuracy in addition to the scale, right? And we've done this without inventing a new clock sync protocol. We're not relying on some centralized control nodes, and we take advantage of all of the existing PTP capabilities in the network. If you want to work with us on this, okay, then get in touch. We are always interested in the opinions of interesting and smart people. And we would also like to conduct some large-scale tests. Okay, of course, we can do this with a virtual host, but we would like to do some tests which are even bigger. If you want to try this, okay, it's not secret or in beta or whatever. You can jump right onto our website and you can download it, and you can get a license, trial license that is runs for 60 days or whatever. It runs on Linux and Windows. And if you do decide to try it, okay, then we'd be extremely grateful if you would tell us what you think about it, because we want to know. And that's it. So what I have now, okay, I know I've been going on for now 70 minutes. Oh, is that actually accurate? I've been going on for a while now. I have a video, okay, which shows sort of a real-time demo of it that I might be able to play.
Yeah, play the video, please. Yeah.
Okay, well, let me see how I can do that.
You can just minimize this and then open your video player.
Yeah, buddy. Maybe. And what about this? We talked about this notion of including media sound or something like that.
It should probably work. Let's see. If not, then we'll figure out how to add the video file, basically.
Okay.
Yeah.
Okay, you can see this?
Yes.
Okay, and can you hear it too? Can you hear me talking?
I can hear you, but I don't hear. Yeah, we can play it back like this, and then I can add it later also.
We can have this one. Have a UTC source. Can you hear it now? Okay, so test host 3 and test host 2. They have.
Yes.
So yeah, here we go. I'd like to just do a sort of demo of the system, I guess, in real time. And yeah, initially I can just tell you about the hosts that will participate in this. So we have 2 nodes that have a UTC source. Okay, so test host 3 and test host 2, they have a UTC source. And then we have 2 other hosts, test host 4 and 5. And yeah, they will get time from the hosts that have a UTC source. And then in addition to that, I'm going to spin up a bunch of virtual machines just so we can see sort of squared forming a network. Now, initially, only test host 3, which has a UTC source, and test host 4, which doesn't, is switched on, and we can just have a look at them. So here is test host 3, and the source of the UTC here is pulse per second input. In fact, this is an NVIDIA Mellanox Connect X6 CAD, which is getting pulse per second from a Grandmaster clock. And then we can look at test host 4. Okay, and we can see that in fact it's receiving PTP set up by squared from test host 3, and we can just maybe turn that to the CLI. So if we first look at the network, Okay, we can see that we're currently connected to test host 3. Okay, this does not speak to whether we're sending time to a particular host or receiving time from it or whatever, or neither of those two. Just that the squared network is formed between those sort of two nodes. And if we want to know if we're getting time, okay, we can look here. This is a list of nodes we take time from, and we can see that that indeed test host 3 is one of them, and we could also do something like show PGP pairs. Okay, here we can see that okay, it's in domain 115. We have an error of source of 5 nanoseconds, and we're running at interval -4. So that's good. And then I think the first thing we'll do is we're just going to start up test host 2, which also has a UTC source. Okay, and then we'll just look at what happens as a result. So I'm doing this on a separate screen, which you cannot see. So that's sort of running now, and we can just have a quick look to see if it appears. Okay, here it is. Okay, and we can see that, yes, it's using hardware timestamping, okay, ENS1, and we have the source down here, okay, it's a PGP feed from a Grandmaster as well, okay, so this is not related to the squared network, it's just a statically configured PGP source. And you can see here the filter kicking in. We zoom in. We can sort of see that the timekeeping is okay. It's a few nanoseconds plus minus. Okay. After the filter kicks in, that obviously improves a lot. You can see we're down into the single-digit nanoseconds now. And then let's go. Let's go back and look at test host 4. And I'll just go to the 5-minute window. So, not a lot has changed so far. We can just have a look at what's going on in the squared network. Okay, we're still not connected to test host 2. Okay, that will just take a little while. We just have to make sure from when we start something up that you know, the time it's capable of giving is worthwhile and so on. So it takes a little time. But I'll tell you what I'll do in the meantime. Okay, I'll switch on some virtual hosts so we can just have a look at them. I'm gonna do this on a separate screen as well. Okay, so I'm going to start up 10 virtual hosts. And this will just also take a little while. Okay, so let's look at the squared network now. Still no dice. So we can see that now we are in fact connected to test host 2. Okay, let's say the squared network at least is there, and okay, yeah, we can see that we have started to also take time from it. Not in an active capacity, it's a monitor-only capacity. And we can see that the local source of error here is quite high, but this will sort of reduce quite quickly. And in the graphical front end, we could just sort of refresh and see that in addition to sort of test host 3, which was there all along, we also now have test host 2, okay, providing time. And if we zoom in, we can see that yeah, it's quite reasonable, and as the filters kick in after a little while, this will get even better. So that's good. And then I guess we turned on these 10 virtual hosts, okay, so we can just have another look at the squared network to see if they've shown up. And okay, indeed they have. So they just sort of joined by themselves. All they know really is about the two sort of initial seed nodes 2 and 3. They don't have a concept of node 4, but you know, because of the peer-to-peer nature of it, then are also connected to node 4, and we can have a look to see if any of them are taking time from node 4, which we're sort of connected to. Okay, and indeed this is the case. In fact, 4 of them are currently taking time from node 4, which is what we're on the CLI of here. Okay, so we'll have a look at those. And one thing I can also just show before we do that is I can show how capacity announcements work. So we can see here the different nodes that are announcing you know, available capacity in quotes to give time in the network. And we can see how many seats they have available, and we can see what the capabilities they are advertising. And in fact, in this particular network here, okay, it turns out that node 4, just as 4, it has a high quality oscillator in it. So we've denominated in the config file that this is the case. Okay, so should we lose our sources of UTC, okay, we can rely on that holdover capacity. And in this particular setup, it's the only host that has that that capability. Now, of course, whilst we have UTC sources, that's not worth a lot. But we'll have a look at that as we proceed. And let's see, here in the front end, we can just see sort of data starting to tick in, and obviously initially these are all virtual hosts, so these numbers will get better as we proceed. And we can also look at them individually. So here some of them, let's see, so for instance, we can see that we're giving time to 221, so let's look at that one. Okay, so here is 221, which was just started up, and in fact, maybe I can just show the configuration file. So all the virtual hosts have the same configuration, and it looks like this. So we can see that we've just enabled DHT as the discovery, and we've given it initially node 2 and 3 as seed hosts. We've told it what interface to use, how many seats to offer to other nodes, how many seats to try and obtain from other nodes. We've configured things like what should be the interval if we're using time from something in an active capacity and if we're only monitoring it. And then all of this stuff down here is just some default values. And so 221, for instance, which we're looking at here, you can see that even though it's a virtual host, we get sort of quite reasonable accuracy. Okay, it's in the low microseconds. And we have one source here, it's another virtual host that it has connected to. Okay, we have it's also connected to node 3, which it is actively using, and it is connected to node 4, which it is just monitoring. And yeah, this sort of distribution of dots is quite normal, so we don't show the dots that are filtered as we do here for monitored nodes. So that's all quite normal. And we can look at another node. Okay, so here's some corrections going on initially when it starts up. But okay, here's an example of a node. So this is node 226, for instance, and it's getting time from other virtual hosts. So it has sort of managed to establish a hierarchy by itself in this fashion, and we can sort of gauge that by looking at again the capacity which is being announced currently. So the route distance is obviously reported to us by the particular node, so we can see that the further out a particular node gets, the higher becomes the cumulative route distance, which is also what you would expect. And then I can just show the reservation system. So here we have node 4, and we can just look at how it's configured. So we have, in fact, here 2 reservation allocations. Okay, the default one, which just requires a minimum preference score of 0, and all of the virtual hosts we started up, they have a preference score of the default one, which is 0, so they've managed to occupy that allocation. And then we have also 4 seats which require a minimum preference score of 500, and there are no hosts which have that preference score yet. So, so that capacity has not been sort of consumed yet. But we're going to change that, okay, because we're going to change, we're going to start up node 5, okay, which does have a preference score that fits into the higher reservation. Okay, so I'm going to do that now. And this is, again, sort of just to showcase that you can hold the capacity in the backhand for, you know, some nodes that you prefer are given a particular preference. So that's currently starting up, and I've started this on a screen you cannot see. So we'll look at that. Let's see, just refresh here. So we've got test host 5. Okay, just starting up now. Okay, so here we go. It's starting to get some time. Let's see. Okay. So here we go. So it's currently taking time from 2 and 3, and obviously it means it has not consumed yet the reservation held for it on 4. I'm sure it will shortly though. Here we go. So now it's getting time from 2, 3, and 4, which is good. And we can just go back and verify that this is the case. Okay. So there we go. So we can see that now we have in this higher tier here test host 5, and this is indeed what we would expect. And we can look again at what capacity is being announced. Okay, so this is pretty good. And then why don't we go ahead and start up another 5 virtual hosts just to show what that looks like. So you can imagine, you know, sort of adding additional hosts to the network. from time to time. So here we go. So I've done that also in the background. And make this one a little bigger. So let's see, show screen work. Okay, here we go. So before we had 10, and you can see that we now have 15 because the last one is 235, and they will also ultimately, establish themselves and start taking capacity from the existing nodes which have capacity to offer, and then they will themselves start to announce that they have available capacity. Here's an example of that. 232 has just come on, and so has 231. And we can see that because they're joining the outer edges of the network, okay, their cumulative route distance is sort of higher, isn't it? Okay, and then what shall we do next? So I think let's look at this host, for instance. Yes, this is a good example. So it has, it's obviously taking time from another virtual host that it's monitoring from test host 3, and it's monitoring test host 4. Now, what we can do is, for fun, we could try and disconnect the UTC source that the test host 3 is getting. So, and we could see what happens as a result. So if we go to test host 3, you remember it's the one that's getting a pulse per second input. So now I'm going to disconnect that pulse per second input. Okay, I've done that. Just pulling out the coaxial cable. And the result of that will be no more pulse per second dots. But it will also mean, obviously, that it can no longer announce the capability that it has a UTC source, because it doesn't have a UTC source anymore. So we'll go back and look at what's the consequence over here at 221, right, which was previously getting time from it. So we can see that it is now electing instead to take time from a different source, okay, because it's, because there was no longer the capability of taking time from the previous source. And another consequence of this is that test host 3, okay, will need to do something to get its time, because it no longer has the pulse per second input. So what it has done, okay, is instead now it has started taking time from test host 4, okay, which makes sense given that it has lost its own UTC source. And this leaves only one UTC source in the network, right, the one which is connected to test host 2. And so what we can do for fun is we can also disconnect the UTC source from test host 2, okay, which will leave us without a UTC source. So what will happen then? Okay, what should happen, I'm hoping this will happen, is, of course, everything should converge around test host 4, because it has the capability of an oscillator. Okay, so it is capable of providing holdover where we lose all of the UTC sources. And what we should also see is that of all the stuff which is, the capabilities in the network, so we can see some of the nodes which are announcing capacity. Okay, we can see that they have you can see the oscillator in their path. So somehow they're all of the nodes that are announcing capacity, that have spare capacity, they're all seeing that high quality oscillator capability in the network, but they also are announcing a UTC source indirect. Okay, and this should change obviously when we remove the last source of UTC in the network. So I'm going to go ahead and do that now, and I'm doing that by unplugging an Ethernet cable, which you cannot see. And then it's going to be interesting to see what happens now. So let's go to test host 4 and have a look. Okay. Yeah, so of course, we can also see that when we disconnected the UTC source on test host 3, test host 4 switched to test host 2. But we have now disconnected the UTC source from test host 2, okay, which means that yeah, it doesn't make sense anymore for test host 4 to take UTC from or to take time from test host 2. So you can see it's just not doing that, okay, which makes sense. And let's see what test host 2 did as a result, okay. Well, test host 2 started to take time from test host 3, which, as you'll recall, is taking time from test host 4. So it means that, okay, everything has now converged around, you know, the oscillator. And let's look at one of the virtuals. Okay, and we can see that, yeah, they're also sort of in the process of finding out where to get time from. And if we look at the capabilities in the network now, okay, we can see that everything is as we would expect, okay, in the sense that we have lost the UTC source capability, which of course in this case makes perfect sense. But we retain the high quality oscillator capability. And so I think, let me check my list. I think that is everything I wanted to just show. Yes.
Lasse, thank you so much.
Yeah, you're welcome.
Let's see if there are any questions. Please open your mic.
I think
and
if you're still hanging on after an hour and a half of this, you're a hardcore time nerd for sure. Yeah.
Yeah, you qualified. Well, again, thanks. We really appreciated that, and I think there's a big value for this community with today's session. So I'm glad we had it, and thanks for staying longer.
Yeah, for sure.
Okay, so with that, we will conclude for today, and the presentation will be loaded to the website, to the wiki website shortly.
Yeah,
thank you, everyone.
Thank you very much for the opportunity. Thank you.
Bye.
Bye.
Thank you for the presentation.